by Tatiana
Chichinina.
Let Vladimir do it.
And that will be on the theory of linear sleep model, revised. So it will have a non-stop 45 minutes, and after that we'll have the second. Okay, thank you.
I have changed a little bit the title of my presentation, and now it is constraints on C13 for shales.
Tatiana, could you use the microphone?
I will speak louder.
Okay.
I will speak louder. I will speak exactly on C13 and shales and physical models, different Poisson's ratios in VTI rock, and compliance tensor for VTI shale. It is a well-known fact that anisotropy in shale rocks can be caused by at least of two factors. The first is for the late microstructure in shale rocks. These are the horizontal clay microparticles or the horizontal platelets, which are parallel and they form the late model at the microscale of rock. And the second is horizontal microcracks. Linear slip model was developed by Mike Schoenberg, and Colin Sayers justifies the linear slip model for shales by the following manner: because the regions between clay particles are expected to be more compliant than the particles themselves are, they can be treated as horizontal fractures. The main topic of my presentation is on the constraints of the C13 parameter in shale rocks. It is very important to get through C13 parameter for a certain shale formation. For example, that is necessary in estimation of the minimum horizontal stress. The overall transverse isotropic model with the vertical axis of symmetry is a conventional model for shale rocks. There are 5 independent stiffness tensor components. For the C13 estimation, it is necessary to know the P-wave velocity at 45 degrees to the symmetry axis. But in practice, the data is always absent for the shales at the 45 angle or arbitrary angle. In contrast to the VTI overall model, the linear slip model has only 4 independent components, and the component C13 is linked to others by this equation. It is the restriction on the C13 established by Schoenberg. Following this formula for the C13, one can estimate C13 in shales using only 3 velocity measurements in shale rock. These are 2 P-wave velocity measurements at the main symmetry directions 0 and 90 degrees relatively the vertical symmetry axis, and 1 shear wave velocity measurement that is so-called CH wave velocity at 90 degrees. However, this approach of using the linear slip model to calculate C13 parameter results in great errors in C13 estimation, as I have demonstrated in my SCG paper last year. And recently, 2 important papers appeared in Geophysical Prospectus on this theme. Last year, there was an interesting paper by Yan, De Hua Han, and Yao, Houston University, physical constraints on C13 and delta for transversely isotropic hydrocarbon source rocks, published in Geophysical Prospectus. The authors of the paper derived formulas for the lower and upper bounds for the C13 parameter. Their constraints on the C13 parameter are based on the following statements. First, Poisson's ratio should be always positive in rocks. That is obvious. And the second statement from their paper is not so obvious. The second statement is they claimed the following inequality for two Poisson's ratios in shale rocks. As you know, there are three Poisson's ratios in VTI rock, and these two are so-called horizontal Poisson's ratios that we can measure in the cylinder sample of rock cut in this manner from the VTI rock. And so, by uniaxial loading of this sample, we obtain two strains, transverse strains. One we can measure in this direction, vertical strain, and the other in the horizontal. And so, dividing these transverse strains to the uniaxial strain, we got two different Poisson's ratios, because this strain, vertical, that is normal to the fracture plane, and this strain that is parallel to this plane are different, and therefore it results in two different horizontal Poisson's ratios. And by the way, the vertical Poisson ratio is measured in the vertical cylinder, and so it is only one vertical Poisson ratio, because if you measure transverse strain in this direction, x and y, x1 and x2, it is equal, because it is the symmetry axis of the VTI. And so, based on this inequality between two Poisson's ratios, the authors of this article derive the following formula for the lower bound of C13. For brevity, I shall name it Young's criterion by the name of the first author of the paper. This year, there was an article by Joël Sarrou. I don't know how to pronounce it. Maybe it is like in Francais. So I pronounce it Sarrou. Is it right? Actually, this paper is the answer to the paper of Yang, Han, and Yang. The author finds out a counterexample that is an opposite inequality between the two Poisson's ratios. You see, opposite inequality. His counterexample is based on calculating of 5 anisotropic elastic constants using Baker's averaging for a thin-layered medium VTI composed by two alternating layers. Finally, Sarrou concludes that Young's constraint for the C13 is not true, because in his medium he obtained the opposite inequality for these two horizontal Poisson's ratios. My presentation is about this contradiction and the way to resolve it, to know correct constraints for the C13 parameters in shales. First, I have found out that Young's formula for the lower bound of C13 coincides with the formula for the C13 established by Schoenberg for the linear slip model. It helps me to resolve the problem of these two contradictory statements. I have reported it in the SHE last year, so this is how I found that these two equations are the same. I I repeat, the equation for the lower bound that was derived by Young, this equation, and the lower equation is the restriction on the C13 parameter, which was established by Schoenberg for this model. To resolve this problem, let me introduce a new parameter, delta C13, which I define as the relative difference between the real C13 measured in shales and the theoretical C13 proposed by Schoenberg for the linear slip model. The delta C13 parameter can be written also in this way below because of the coincidence of the C13 minimum of Young and the C13 from the linear slip model, as I have discovered. I studied the parameter delta C13 using mainly three articles of all. There are published data on shales as well as physical modeling data from other two articles. Let us begin with the results on shales. This is famous article of Thompson, and I used this data from this article shown at the vertical axis, and is the number of shale rock samples fallen in the certain interval of the delta C13 parameter, given in percent. The negative delta C13 parameter corresponds to the criterion of Young, and the positive to the criterion of Sarov. The majority of the samples falls in the interval of negative delta C13 parameter. So we can conclude that the shales of Thompson correspond more to Young's criterion. So this criterion for the restriction for the C13 parameter would work for these shales from the period of Thompson. By this table, I summarize what we have. There are three different constraints for the C13. The first is Schoenberg's restriction on the C13 for the linear slip model. Note this zero delta C13 parameter for this case, because these two C13 coincides. I mean, Schoenberg supposed that C13 must be equal to his C13 linear slip, and therefore the difference between them is supposed to be zero. And I analyze it in terms of these two Poisson's ratios. So for Schoenberg's restriction, these two Poisson's ratios are equal. Actually, the equality of these two Poisson's ratios required for the linear slip model is an exotic case in real data. That is, almost never occurs in practice in real shale rocks. This equality takes place only in the theoretical linear slip model devised by Mike Schoenberg, which was developed furthermore by Colin Cyrus for the application to shales. The physical meaning of these two Poisson's ratios in terms of the compliance tensor, I shall give you later. These are two Poisson's ratios estimated in real rocks using the data from these three articles. The first is by Thompson, the second is Johnston and Christensen, and the third is from Wang. There are good tables with all the all the 5 parameters, including C13 in this paper. That is why I did it. The line divides the variety of all considered shales samples into 2 groups. The first group is for the shales of Saru, the upper region in the graph, which includes the shales obeying the criterion of Saru, this inequality of the 2 Poisson's ratios. And the lower region is for the shales of Yang. And on this line, we have equality of these 2 Poisson ratios, so it is the linear slip. For the linear slip model, the equality delta C13 means that both Poisson's ratios are equal to each other, as shown by this line. The line with inscription delta C13 separates the variety of Poisson's ratios into 2 groups: the shales of Saru with positive delta C13 and the shales of Yang with negative delta C13. For some shales, Yang's criterion works well, as shown here. These are Thomson's shales from his paper and the shales from the paper of Johnston and Christensen, shown here. For other shales, the counterexample of Saru is better. And here you can see this is the line where delta C13 is equal to 0. And you see that almost all the estimates of the parameter delta C13 is negative, so it suits very good for Yang's criteria. These examples approved the criterion of Yang, Han, and Zhao that they have published in their paper. But there are very difficult results for the shales from the paper of Wang. In contrast to the previous 2 examples, now only a smaller part of shale samples meets the criterion of Yang. And whilst the majority of them, of the delta C13 parameter, exhibits positive delta C13 parameter, that is the criterion of Saru. One's shales represent very diverse collection. For example, there are Africa shales and several samples from the North Sea and Gulf Coast shales which meet the criterion of Yang. However, the other shales, which are the majority of the samples considered, they fit the criterion of Saru is better for them. It includes the brine-saturated Gulf Coast shales, the hard shales, the siliceous shales, and the shaly coals. Finally, according to the results of the analysis, we can conclude that the criterion of Yang and its counterexample of Saru are both true for shales. For some shales, Yang's criteria works well, as shown here. These are Thomson's shales and shales from the paper of Johnston and Christensen. However, for other shales, the counterexample of Saru suits better, as for the shales of Wang. In addition, I have also studied North Sea mud rocks from the article of Morton Jacobsen and Johansen. The results of the analysis of the delta C13 parameter are shown here. The mud rocks of Morton Jacobsen exhibit similar anisotropic properties of the VTI type as the shales of Wang due to horizontal alignment of the micrograins. Interestingly, in the diagram for the mud rocks, there is a similar 2 maximum trend in the delta C13 distribution as that for the shales of Wang. Namely, one maximum is for negative delta C13 parameter and the other is for the positive. Moreover, there is another obvious similarity in the predominance of the rock samples falling into the interval of positive delta C13 parameter that meets the criterion of Saru. In addition, I studied carbonates and sandstones from the paper of 1. We can see almost symmetric delta C13 distribution near zero in both graphs. Here, for sands, the delta C13 parameter is the maximum is only minus 5%. It is almost zero. It is a difference. It is in contrast that we had seen with the shale rocks. And it can explain by the following. As is known, sandstones and carbonates have weak anisotropy. For example, following Wang, the average Thomson's parameter epsilon and gamma are small for sandstones. Moreover, for the carbonates, they are even smaller than for sandstones. Whereas for the shales, the anisotropy parameter are 10 times greater. So, sandstones and carbonates are almost isotropic, and they exhibit very small delta C13 parameter. I can explain it in this way. Note that for isotropic rocks, the condition on C13 for the linear slip model automatically works, and therefore delta C13 is zero. Here it is a very simple proof of this statement. Therefore, in a weakly anisotropic rocks, such as sandstones and carbonates, the average delta C13 parameter should be close to zero, and so that we have seen. And now let us consider the analysis from the physical modeling with the plate models. They are interesting. There are the results from the data from the paper of Xu and Schoenberg that demonstrates that all the delta C13 are positive. And so this data from this experiment suits better for Saru criterion. And other observation is that the relative difference between the measured C13 parameter and the theory predicted by Schoenberg is very small, up to almost 4%. So this experiment is in a very good agreement with the linear slip model of Schoenberg. It is the best experiment that I have seen that proves the linear slip model. Now, let us consider the results which I have obtained from the data of the PhD thesis of Mehdi. That is physical modeling data with plexiglass plate model. He realized it in two variants. The simple plexiglass plate state model and the model with rubber inclusions between these plexiglass plates. And so now we see how it works. Here you can see his two published works on this experiment. And in his paper published in Geophysical Journal International, you cannot find any data for the incidence angle 45 degrees that is necessary for C13 estimation. Because Mehdi has taken it away after my revision of his article. I was reviewer of his paper. When I was reviewer of his paper, pointed out to a great difference in Thomson parameter delta, which can be estimated by two ways. The first way in the delta estimation was with the use of the C13 measured in the experiment. This is a red curve in this lower. And the second way is to use the C13 parameter calculated from Schoenberg's formula. And there was a great difference in the results for the anisotropy parameter delta, and I asked him to explain this difference. Therefore, I have written a letter to Merdifar about it, but he could not even explain why does this difference takes place, and so he decided not to show the data at the angle 45 degrees, and unfortunately he took it away from the paper, and now all the original experimental data on the velocity measurements at the angle of 45 degrees are absent in his published article in the Geophysical Journal International. However, using the original experiment data published in his PhD thesis, I studied the delta C13 parameter dependence on pressure. There is a critical pressure point, P0, the threshold, at which the delta C13 parameter turns to 0. That is, Schoenberg's restriction on the C13 parameter is satisfied only in this point at this certain pressure P0. As you can see, for the initial pressures, which are smaller than the threshold pressure P0, the criterion of Young takes place, that is negative delta C13 parameter. Then, passing of the threshold pressure P0, for greater pressures, the delta C13 parameter turns into the positive. That means the counterexample of Saru. I can give the following physical interpretation for this. At the threshold pressure P0, the contact areas between the cracks are subjected to the transition to a different qualitative state corresponding to the linear slip model. That is because of partial closure of the cracks, so that the contact areas between the cracks become forming thin layers which are compliant and soft. These are the so-called welded contacts, for which the cracks can be represented as the layers of weakness following the linear slip model. At this point, P0, the displacement discontinuity boundary condition of Schoenberg developed for the linear slip model works well. Actually, the cracks can be represented by infinitely thin soft layers embedded in the host rock. Therefore, Baker's averaging for the thin layered model with the two alternating layers can be used as for the counterexample of Saru that was the answer to the paper of Jan Han and Jan. Now let me summarize what we have at the moment. Saru found the counterexample to Jan's criterion and therefore concluded that Jan's constraint for C13 was not true. However, I believe that these two are both true, are both right, for certain shales under certain pressures. For the first kind of shale rocks, which I named Jan's shales, I suppose the crack fact is responsible for the inherent inequality of these two Poisson's ratios. And for the shales of Saru, I treat the cracks as thin compliant layers, as in Schoenberg's linear slip model. I name it the layer factor that is responsible for the opposite inequality of two Poisson's ratios. Now, I would like to show you my pictures and these models which I have made for you for the explanation, for the possible explanation of the physical meaning of these two Poisson's ratios and these two possible inequalities between these Poisson's ratios. May I remember you that Poisson's ratio can be defined as transverse strain divided by the axial strain under uniaxial load, so that the cylinder shrinks along its axis and simultaneously it expands at the cross section. But we deal with this horizontal cylinder. In transversally isotropic rocks, there are three Poisson's ratios. These are one vertical Poisson ratio, which we measure in the vertical cylinder, and two horizontal Poisson ratios. In addition, there are two Young's moduli. In total, we have 5 independent parameters, 3 Poisson ratios, and 2 Young modulus that identify transversally isotropic compliance density. For measuring these 3 Poisson's ratios, it is necessary to have 2 cylinder rock samples. One is vertical cylinder, its axis coincides with the vertical axis of transversally isotropic rock, and the other is the horizontal cylinder. Given the vertical cylinder loaded by the vertical uniaxial stress sigma 33, we can measure the vertical Poisson ratio and vertical Young modulus. And by uniaxial loading of the horizontal cylinder, by the horizontal stress sigma 11, it is along the x1 axis, we can obtain 2 different horizontal Poisson ratios and 1 horizontal Young modulus. Let us consider the transverse strains as the cross section of horizontal cylinder. Cross section, this under uniaxial loading sigma 11. If you measure the transverse strain at the vertical direction, here, and in the horizontal direction, they will be different. So these 2 horizontal Poisson ratios are different. This ellipse is this ellipse. This is shown here. Is for the deformation pattern corresponding to Young's criterion. This is the cross section of the horizontal cylinder sample of the VTI rock under uniaxial loading by the horizontal compression stress along the x1 axis, so that the cylinder shrinks along the axis and simultaneously it expands as a cross section x2, x3. This expansion is anisotropic in the form of ellipse. You can see these 2 unequal transverse strains at 2 mutually perpendicular radial directions. The strain epsilon 33 at the vertical x3 axis is larger than the strain epsilon 22, following the criterion of Young. Therefore, as you can see, at this deformation pattern, the largest axis of the ellipse points the vertical x3 direction, and therefore the inequality of Poisson's ratios takes place that is claimed in the paper of Young and his co-authors. I believe that the possible a possible physical mechanism for Young's inequality of Poisson's ratios can be interpreted as the opening of the cracks due to the uniaxial stress. You see, these cracks are open. You see these gaps when I put it to the uniaxial stress. Here I drew these imaginary springs just for the illustration that the distance between 2 opposite crack sides has increased like this under the loading stress sigma 1. Therefore, it vertical x3 direction, then at the horizontal x2. By this manner, I can explain why this Poisson ratio, nu1 3, is greater than z1, nu1 2. That is the criterion of Young. I painted another picture for the explanation of the same criterion of Young, so maybe you would like it more. As you can see, this is a penny-shaped crack embedded into the host rock. The upper picture shows the crack before the loading, and the lower picture is for the same crack after the uniaxial loading. The crack shrinks at the uniaxial loading direction, that is x1 direction, by the uniaxial stress sigma 1,1, and simultaneously it expands at the vertical direction, x3, and therefore the gap between the layers increases due to the crack disclosure, and that means that total effective medium deformation epsilon 3 becomes greater than epsilon 2, and that is why the inequality between two Poisson ratios take place that is created by Jans with his co-authors. Now let us consider the possible physical meaning for the counterexample of Sarov. Now the largest axis of the resultant ellipse is pointing to the horizontal x2 direction because of the horizontal strain epsilon 2 greater than the vertical strain epsilon 3. For the counterexample of Sarov, I can explain the physical meaning of the inequality between two Poisson ratios nu1 3 is less than nu1 2 using the model composed by two alternating layers as shown here. One layer is soft and compliant, and the other is hard and stiff, as in the linear slip model for shales, for example, as in the paper of Schoenberg and Buer. These compliant layers represent cracks treated as planes of weakness in the linear slip model for shale rocks. This is the cross-section view at the vertical plane x2, x3 of the VTI rock sample in the form of cube after the uniaxial loading by the compressional stress sigma 1,1. All the compliant layers are stretched in the bedding plane under the uniaxial loading. Therefore, the horizontal stress epsilon 2 becomes larger in this case than the vertical strain epsilon 3. My exaggerated sketch shows large elongation of all soft layers at the x2 direction. Now it becomes clear that the total strain epsilon 2 at the bedding plane will be greater than the strain epsilon 3 at the normal to bedding plane direction. It leads to the inequality of two Poisson ratios derived by Sarov. Thus, both inequalities between two Poisson ratios are true and can take place in shale rocks. The crack factor, as I named it, can explain the physical meaning of Young's criterion. That is the crack opening under uniaxial loading by stress sigma 1,1. In addition, the layers factor, as I call it, is responsible for the physical sense of the counterexample of Sarov. That is the compliant layer stretching under the uniaxial loading. Now, let us consider the compliance tensor for a VTI shale rock. Given the inequality of Poisson's ratios claimed by Young with co-authors, the nu1 3 is greater than the nu1 2, one can infer that the compliance tensor components S1 3 should be greater than the component S1 2. It can be seen from the symmetric components S21 and S31, as you see here, because the same horizontal Young modulus enters in the both these components, and so you see that the inequality between the Poisson ratios, nu1, 2 and nu1, 3, determines the inequality between the corresponding compliance components. The absolute values, because of the sign minus of these components. So you see that this inequality nu1, 3 is greater than nu1, 2 means the inequality of these two compliance tensor components S1, 3 is greater than S1, 2. Note that for the linear slip model, there is equality of two compliance tensor components. Now I shall show you this. First, let us consider the example for Saru criterion. And for Saru criterion, it is vice versa. From the inequality of two Poisson ratios, we can see that the same inequality is for the absolute values of the compliance components. And as you maybe know, the compliance tensor for the linear slip model is the mathematical sum of the isotropic compliance tensor for the host rock and the additional tensor for fractures, which contains excess fracture compliances Zn and Zt. Note that for the linear slip model, there is the equality of two compliance tensor components, S31 is equal to S21 and S12 is equal to S13, because of the inherited of the isotropic compliance tensor for the host rock. This so the Poisson ratios nu1, 2 and nu1, 3 now are equal to the Poisson ratio in isotropic rock, and so they are equal in the linear slip model. In the linear slip model they are equal. But it is not physically plausible, because they cannot be equal in the transversal isotropic rock, and that is contradiction of the linear slip model, and the stiffness tensor can be obtained as the mathematical inverse of the compliance tensor. The equality condition for two compliance components S13 is equal to S12 now is transformed into the restriction for the C13 component in the linear slip model. I would like to remember that I have introduced a new parameter delta C13 as the relative difference between the real C13 estimated from the real data in shale rocks and the theoretical C13 established by Schoenberg for the linear slip model. In conclusion, I would like to remember that by the use of the new parameter delta C13, I have carried out the statistical analysis for the C13 component in different shales, that the negative delta C13 parameter corresponded to the criterion of Young, and the positive to the criterion of Saru. The analysis proved that both considered inequalities between two Poisson ratios could take place in shale rocks due to their different microstructure that I named the crack factor and the layers factor. As well, that it could be due to different pressure conditions. So, in addition, I have found the correlations with the compliance tensor components S13 and S12, and these key factors can divide this all the shales into two groups. One meets the criterion of Saru, and the other meets the criterion of Young, Han, and Lam. So thank you very much. That's all.
Okay, thank you very much. It's for me very educational. Okay, we have plenty of time for discussions and questions. Yeah, but we still have time.
So I actually follow this very closely, the response between them. Jan's actually provide a response back to Saru's comment in geophysical prospecting as well. I'm not sure you have both seen that. They basically said that, well, kind of agree with you that like the relationship that they drew in the first place was the parabole from what they observed, and they couldn't provide any explanation like you did. So very nice work. And I just want to point out one thing, very small. So you show a bunch of papers that collect CIJ measurements. I'm not sure you got a chance to check the positive definiteness of the stiffness tensor, because they use some of those as well. And sometimes
Use what? Can you look?
the positive definiteness of the stiffness tensor, so it doesn't criteria for those, but in an energy constraint, so you don't want to violate that for sure. Some of the old measurements actually do violate those.
Oh,
So
is that right? Like
Yeah.
some of the examples in my 86 paper?
there are some of those, yes.
Yeah, so not my fault.
Yeah, I know.
Other people's
Yeah.
data.
Right. That's just a disclaimer, I guess.
That's interesting, very
Yeah,
interesting.
because I
You
use
did
it.
not check it, Leon, right?
You
It did not occur to you to check.
I wasn't smart enough to check.
So some of those should be thrown away, I guess. And but I guess the overall analysis should remain pretty much the same. Because there are not many of those. Just
You know, that's worthy of a publication in geophysics to explain to everybody what we mean by positive definite stiffness tensor, and give some examples of violations in the data in the literature. That would be very good.
This is not because like the first time I worked on this, and I met with Joe Dellinger, and he discussed the condition explicitly in his thesis in the appendix. And he was the first one who found this out. I was not the first one. And
Is that in his thesis?
He didn't. The constraint and everything is in his thesis, but he found out, but he didn't actually put it out there saying which one is actually wrong. But there is an explicit condition on all of this.
The problem with Joe is he thinks everybody is as smart as he is, and very few of us are.
Michael in his book expanded very, very.
But I mean, it is matrix theory, right?
Yeah,
You have
exactly.
positive.
Right.
I mean,
I have to
read the textbook of linear algebra.
Well, here's an example of it. Tatiana said, of course, Poisson's ratio has to be positive for isotropic rocks. Well, that's not the case. The criterion is positive definite stiffness element, stiffness matrix for isotropic rocks, and you can allow Poisson's ratio as small as -1. And I used to have a sample of material with a negative Poisson's ratio, but it evaporated on me sometime doing when my back was turned. And it is true that they're rare. The example I had was an artificial sponge. And you could squeeze it like this, and it would contract laterally.
But micropunch.
Tatiana, you have a nice example of unphysical rocks on your slides. If you can show this delta curve, or the red curve
The delta curve.
you have deltas on one of your slides.
You will-
Kind of question.
Let us see. You will tell me when
It's not your fault, because it's from Far's paper, or dissertation.
Ah.
If you can show that the plot was
Uh-huh,
deltas.
uh-huh, uh-huh,
yeah.
uh-huh, uh-huh, uh-huh. it is not from first dissertation. He could not even explain. I have obtained this result, and I asked him, why these two deltas, it is mine, it is of mine. This delta is of mine. He does not know how to explain it. And
But
so
he used his CIJs, right?
No. Look, in his PhD dissertation, he has the data on the velocity at 45 degrees. And I calculated these two deltas. One for the linear slip model, and the other is real from measured data. And I asked Mehdi, why it is the difference? He could not explain me. And then he quoted the data for 45 degrees from this paper of Journal Geophysical International. So he could not find any data for 45 degrees and only for 0 and 90. And he used the formula of Schoenberg to calculate delta parameter C13 and from C13 delta to calculate compliances. So it is erroneous. So
what I mean here is if you look at the red delta curve, one of the values is like 1.3 or something. So that's a non-physical rocks. There's a constraint on the maximum value of delta that's violated here. It comes from the constraint. It comes from the constraint on the maximum value of C13. It can be calculated from the constraint on delta. It's very difficult to create a rock for which delta will be greater than U.
I think that it was not enough pressure between the grease plates, and so each plate was like it is homogeneous medium. No, it is not like an effective medium that can be identified by the linear slip model, and that is why delta, which is the parameter for weakly anisotropic medium.
No, it's not the parameter for weakly anisotropic medium. It's a parameter for any term.
Okay, but it does not serve for discrete plates because the pressure was very few. You see, it is only 2 megapascals that results in the anisotropic parameter delta greater than 0. So this model does not serve for less pressure.
It is not a solid, basically.
It is not a solid. It is like discrete plates. And that is my explanation.
Under the assumption of positive Poisson ratio, delta cannot reach more than point.
It has nothing to do with Poisson ratio. The constraint comes from the fact that strain energy function is positive. And then there's an inequality for C13 can be calculated into the constraint. So that's my good correction. Yeah, so
Okay, one question. So all the experimental data were obtained in the laboratory at ultrasonic frequencies. So I'm wondering if it's important that these are very high frequencies compared to seismic frequencies. If the relations could be different at lower frequencies.
You know that actually in well-logged measurements they cannot obtain C13 parameter, and that is why they use the data from ultrasonic measurements in core samples, and so they automatically use this C13 if they have it, because it's rarely in the shales they can cut off along the 45 degrees, but they use it, and I think that without any calibration they use C13 that obtained in the ultrasonic frequencies.
Still questionable.
So I think,
Sorry, we have.
Sorry.
Please.
Oh, just follow up to that. So all of these calculations for C13 are done on core measurements. Is that a P-wave computation only, or is that using P and SV set estimates?
To obtain C13, it is sufficient to have 3 measurements of P-wave at 3 directions, 0, 90, and 45 degrees. If you have got SV wave, so you can measure this SV and these 3 directions. But it's commonly used P-wave because it is a problem of separating of this share to share. Also, they use pivot.
Yeah, so Leon, one of your colleagues at UH in Jesnikov's class, or your head of paper, when they showed that with a 1% error in the cutting angle for C13, that is, it's at 44 or 46 degrees, you can have
I
a
know.
40% error in measurement. So
Right, you are.
Even using
40% error in the calculation of delta. You get 40, you get BP 45 accurately, but it messes up your calculation of delta. I mentioned this in my 1986 paper, how unstable that is. Yeah.
Okay.
That's-
Tatiana, thank you very much. Leon, you want to say one point?
Tatiana, before you leave, could you go back one slide? And you can see as far as experimental setup. And so he was uncomfortable with the 45-degree results, uncomfortable with the reliability. And when, in response to your criticism and criticism of others, he decided that he probably should be not published. So that's why it's not in the paper in JGR.
Maybe, but I thought it was because he could not explain that.
Well, he had no confidence in the data, and he couldn't explain the data because.
He couldn't explain the difference between two measurements, between two ways of estimation of C13 constant. While one way is using the linear slip formula of Schonberg, and the other is the real measurement. He couldn't even explain theoretically why it is so it means
Tatiana, thanks again. We'll have after the